convergence and uniform convergence. Uniform convergence is the better kind of convergence. It's the nicer kind of convergence, because it's saying that the sequence of functions, they're converging to the limit function at some more or less equal rate across the whole of the domain of the function. Okay? So it's kind of orderly behavior. Everywhere in the domain is getting, the function values are getting closer and closer to the limit function values within the same rate. Okay? Pointwise convergence, the weaker form of convergence, which just says that when you look at one point in the domain, the sequence of function values at that point converge to the limit function value without any reference to the other points in the domain, except that separately they form convergent sequences as well. Well, then it's possible for the sequence of functions to converge to the limit function, but at very varying rates. And the rate can kind of explode or get arbitrarily slow as you get to points that are kind of at the edge of the domain, or points near points of discontinuity. And that can cause problems, and we saw the problem in the initial example we looked at when we think we can differentiate the limit by taking the limit of the individual derivatives, and we run into problems there. So we ran into the contradiction here, this line 1 equals 2 times 1 minus 1 plus 1 and so on. That's plainly a contradiction. We ran into that contradiction because we assumed that we could differentiate the limit function by taking the limit of the individual derivatives, or an equivalent form of that is thinking that we could differentiate an infinite sum of functions by taking the infinite sum of the individual derivatives. Of course, this is talking about a limiting process, although you can't see the word limit there, but we're looking at an infinite sum. And how do we define the value of an infinite sum? We define the value of an infinite sum as the limit of its partial sums. So although you can't see it, there is a limiting process going on both sides here, because an infinite sum is defined as the limit of the sequence of partial sums. Okay. So anyway, so we mentioned these two theorems at the end of the last lecture, so this is where we're starting now. Theorem 3.6 gives us easily recognizable conditions for when the convergence of the Fourier series will be uniform. We ask that the function be continuous over the interval minus pi to pi, so it doesn't make any discontinuous jumps, although we do allow sharp corners on the function. So it's the derivative of the function can be discontinuous. Can make sudden changes in its rate of change, but not in its value. And we also ask that the function be properly periodic of period 2 pi, so that it agrees on the endpoints of the interval. So f of minus pi should be the same as f of pi. If all those conditions are satisfied in theorem 3.6, then we will know that the Fourier series does converge uniformly to the limit function. And then we have this result, Parseval's theorem. And I drew the analogy with the much simpler result about vectors in 3 dimensions, that the norm of a vector is the square root of the sum of squares of its components, or the square of the norm of a vector is the sum of the squares of its components. Well, Parseval's theorem is the kind of analogous statement to that for Fourier series. This thing on the left-hand side, we've got the integral of the square of the function. That's the inner product of the function with itself. So this is, in this kind of linear algebra language, extended to this infinite dimensional vector space. This is the square of the magnitude, more or less, on the left-hand side. We've got this scaling factor of 1 over 2 pi here. On the right-hand side, we do more or less see the sum of the squares of the Fourier coefficients, except there's this kind of confounding factor of 1/2 here. Well, that's there because this factor is over here, and the basis functions we're using, while they are orthogonal to each other, they're not orthonormal. The basis functions we're using don't all have magnitude 1 with respect to the inner product. So that messes up the details a little bit, but at a rough glance, this equation is saying that the inner product of the function with itself is the sum of the squares of the Fourier coefficients, or is strongly related to the sum of the squares of the Fourier coefficients. So let's just have a brief look at how this is proved. And it's basically just an application of this property of uniform convergence. Yeah. Sorry? Analogous, just drawing connections between different things. So we're familiar with that idea that the norm of a free vector is the square root of the sum of the squares of the components. This statement, Parseval's theorem, looks similar to that, but in the context of this infinite dimensional vector space. So this is Parseval's theorem. Looking at the proof of it. So I think, so if you see on the left-hand side of Parseval's theorem, this is the theorem on page 66, there is, we have 1 over 2 pi times the integral of f squared. Well, I'll just leave off the 1 over 2 pi at the moment and just consider this integral from minus pi to pi of f of x squared dx. Okay, so I'm leaving off the factor 1 over 2 pi for the moment. Well, what we're going to do is, so this is the square of f times f. So what we're going to do is replace one of the f's with the Fourier series. Okay. So we'll have f of x multiplied by itself, but now instead of writing f of x, we write the Fourier series. We have half of a naught, the sum n equals 1 to infinity, an times the cosine of nx, plus the sum of all the bn's multiplied by the sine of nx. And this integral is all with respect to x.
Where did you get that?
Sorry?
Where did you get it?
Well, we're just, the statement of the theorem says to assume that f has a Fourier series. So this is a Fourier series for f. So I'm still saying this is the integral of f times f. But now the second f I've written as the Fourier series. But now what we see there, I mean, if you think of multiplying this f into this square bracket, we've got an integral of a function here, and then an infinite sum here, and then added to another infinite sum. But we're told that the convergence is uniform. And in the same way, I mean, I didn't mention integration so much before. We talked about differentiation. But in the same way that uniform convergence allows you to take the derivative of an infinite sum as the infinite sum of the individual derivatives, so too for integration. Okay? Integration very much follows the same properties in relation to uniform convergence. So we can say that since the convergence is uniform, the convergence we're talking about is of the Fourier series to the limit function f. We can interchange the integration and summation operators. Now remember, normally if this is just a finite sum, there's no problem with interchanging the order and saying the integral of the sum is the sum of the individual integrals. That's just the basic linearity property for finite sums. But these aren't finite sums, these are infinite sums in general for these Fourier series, so we need to have uniform convergence to allow us to interchange those two operations. So this is the justification for what's coming next. So we'll have the integral of a half a naught times f. But we'll bring the half a naught out here to the front of that integral. So that's our first integral. So remember, on the previous line, I've got an integral of a giant sum. And now I'm going to write it as the giant sum of the individual integrals. So then we've got all the integrals corresponding to the cosine functions. So this is going to be the integral of f times an times cosine nx. Well, I'll take the an outside, that's just a constant. Sorry, the an has to stay in here, inside the summation, so it depends on n. But I've got the integral from minus pi to pi f of x times the cosine of nx. That integral with respect to x. And then I've got the same thing, but dealing with the sine functions. So the infinite sum of bn times this integral f of x times sine of nx with respect to x. So what I've done there is, well, okay, initially I've multiplied out that large square bracket, multiplied each term in it by the function, by the term f of x. And then I've done this move, that whereas I've got an integral of a giant sum of the previous line, I've now got the giant sum of the individual integrals. And that's justified by the uniform convergence. But now it is, we can see what to do. Each of these integrals that are here, we recognize, okay? The integral of the function across the range, across the domain minus pi to pi, that is exactly half of a naught. Okay? When we investigated Fourier series, initially we arrived at the basic formulae for the Fourier coefficients. The constant coefficient a naught was given as a half of a naught was this integral here, integral from minus pi to pi of f of x. The coefficient an was equal to sorry, brain freeze. Yeah. The coefficient an was given by 1 over pi times this integral. You look back to Fourier series coefficients on page 60. This integral here, the integral of f times the sine function, that gave you the Fourier coefficient b. What we're looking at here is 1/2 of a naught times this is pi times a naught plus the infinite of an times pi an. Then the next sum from n equals 1 to infinity of bn times pi b. And this is just 1/2 pi a naught squared plus pi times the sum from n equals 1 to infinity of the an's all squared plus pi times the sum from n equals 1 to infinity of the squares of all the b's. Yes, so the justification is with reference to the Fourier coefficient formulae on page 60. So this is using the formulae on page 60. Okay, because bn is exactly this integral over, or 1 over pi times this integral. And an is 1 over pi times the integral of f times the cosine. So from start to finish there, what have we got? Right up here at the top, we've got the integral of the square of f, and down here we have the required sum of the squares of all the coefficients. And then dividing both sides by 2 pi, will lead to the required formula. So from this equation, we get the desired result. So if I'm just having a moment of doubt, then shouldn't that require then that, because we're dividing both sides by 1 over 2 pi, get a quarter a naught squared. Yeah, sorry, yeah, let me get a half. Yes. Sorry, just had a brain. Some brain pieces. Okay? So by dividing both sides by 2 pi. Okay, so let's take a look at an application of this. So one application we can get out of this is that if we see a function which has interesting Fourier coefficients, then an application of this result will allow us to evaluate the sum of the coefficients. And if the function is nice enough so that we can evaluate the left-hand side of Parseval's theorem, which is the integral of the square of the function, we're able to evaluate that. Then applying Parseval's theorem should give us, or could give us, an interesting result about the sum of the infinite sum of the Fourier coefficients. So this is the kind of thing that's done in example 3.9, which is next. So example 3.9 deals with what's called a halfway rectified sine function. What is the halfway rectified sine function? Well, these are terms from kind of signal processing. But if you look at it on the interval minus pi to pi, it's defined there in the example. On the negative half of the interval, it's just 0. So this rectification is this process of kind of cutting off the signal on part of the domain. And then in the positive half of the domain, we're following the function sine. See, it's defined as sine of x for x between 0 and pi. So sine of x between 0 and pi goes on this kind of a journey like this. We've got the maximum value of 1 there. Now, by periodic extension, then, this pattern would be repeated across the rest of the domain. 0, then you got the sine wave, 0, you got the sine wave, and so on. And the same thing on the negative half, 0, and sine wave, and so on. But this just continues across the whole of the domain. These are the points pi, so 3 pi, 4 pi, 5 pi, etc. So that's the function we're talking about. And the first thing to do is to recognize that we can. Sorry? I missed 2 pi. Sorry, yeah, that's 2 pi, that's 3 pi. Sorry, yeah. 2, 3, 4, 5. Now the first thing to do is to check that the convergence here will be uniform. And we can check that by comparing this function to the conditions in theorem 3.6. Okay? Those conditions said the function had to be continuous. Well, is this a continuous function? Yes, it is. It's never making any discontinuous sudden jumps in value. It's varying continuously. Its first derivative was allowed to be piecewise continuous. And yeah, the first derivative is not continuous. Because if the function comes down here, for instance, it's got a slope of nearly -1. It's got a slope of -1, and then instantaneously the slope changes to 0. So the first derivative of it isn't continuous, but it is piecewise continuous. The first derivative is changing smoothly across the sine wave, and it's -1 here. It suddenly jumps to the value 0, and the first derivative is held at a constant value 0, because the function is flat here. That's all continuous. But then it suddenly jumps from the first derivative of this. It's got value 0 here, because it's been flat, but then suddenly it's increasing at a rate of 1. Because the derivative of sine of x at the origin, derivative of sine of x is cosine of x at the origin 0 is equal to 1. So its first derivative is jumping from a value 0 to suddenly being 1 here. But it's piecewise continuous. The first derivative is continuous everywhere except at these sharp points on the graph. Okay. And it is properly periodic. It is agreeing on the endpoints of the domain minus pi to pi. The function is 0 on the left point, minus pi, and it's also 0 on the right point, pi. So this does meet the conditions. This does meet the conditions in theorem 3.6. So the convergence is uniform. Now, its Fourier series is presented to us here. We're not going to derive the Fourier series from scratch, but you can do that separately. So it meets the conditions in theorem 6. So the convergence of its Fourier series, f of x, so this is the function f of x. Now it's 1 over pi, that's the constant coefficient. It's a half of sine of x. So there's only one sine function in it, but then there's an infinite amount of cosine functions. And this is a minus. We've got 2 over pi, and then this infinite sum. N equals 1 to infinity of 1 over 4n squared minus 1 times the cosine of 2nx. So we're only picking up the cosine functions for even multiples of x. Okay. Well, I got all that from the question. This information is just presented in the question. But this is the Fourier series. But you can go through the normal process we've been going through to obtain Fourier series, and you'll be able to derive this Fourier series for yourself, working with that function f. Okay. So let's finish the sentence. Yeah. So the convergence of this is uniform. So I can put in as an extra exercise is derive this Fourier series for x, for f. We won't do that now because now we want to just observe this application of the Parseval's theorem here. Well, let's try and pick out in order to perform Parseval's theorem, we're going to want to clearly identify what the Fourier coefficients are. So the Fourier coefficients here are A0 is, well, the constant coefficient there is 1 over pi, but in the way the notation is set up, the constant coefficient is a half of A0. So A0 is 2 over pi. Okay, the way the conventions were set up, the constant coefficient in the Fourier series is always presented as a half of A0. So A0 here is 2 over pi. The constant term there is just 1 over pi. And there is a B1 because you do have sine of x. And B1 is a half. The half times sine of x. But all the other b's are 0. Bn is equal to 0 for n bigger than or equal to 2. So there's no other sine functions in the Fourier series. What about the ANs? What are these coefficients of AN? What are the coefficients of the cosine functions? Well, you see, we see cosine of an integer multiple of x, but it's only even integers. It's 2 times n times x. So we don't see any. Actually, I'm going to change to an here, just not to confuse ourselves with the n used there. So the coefficient is 0 if m is odd. Zero when m is odd. But when n is an even number, then we see it's minus 2 pi, minus 2 over pi. Now what's written there is 4n squared minus 1. But if we're letting n be an even number, then n is standing for the term 2 times n there. What we see there is the square of 2 times n. It's 4n squared, so it's the square of 2 times n. The square of 2n. So this is just n squared. So this becomes m squared minus 1 here. And that's the term, that's the Fourier coefficient an when n is even. So we can see clearly what the a's and b's are. Just extracting them or picking them out of the Fourier series given in the question. Yeah, that's just by mistake. I just put the comma down twice. I hadn't realized. Gap is not significant. Okay. Now, since we have that the convergence is uniform, by checking the conditions of theorem 3.6, we can apply Parseval's theorem. So we can apply Parseval's theorem here. We know the convergence is uniform. We've identified all of the coefficients. We've got them described based on their indices. Indices is odd or even and so on. So the left-hand, what's the left-hand side of Parseval's theorem is this term 1 over 2 pi times the integral from minus pi to pi of f of x dx. Sorry, the square of f of x. Well, how do we work? So we want to evaluate this now for this particular function f, the function f that we're dealing with. So that's what the left-hand side of Parseval's theorem looks like. Well, so we're integrating from minus pi to pi. But you see, all the time for every x between minus pi and 0, the function f is just 0. So it's not going to contribute anything to the integral. So you can just forget about the negative half of the integral. You don't need to bother integrating from minus pi to 0 because you're only going to pick up 0. You're just going to be squaring 0. You only need to integrate over 0 to pi, and in that case, you're integrating the square of sine. Okay, the integral of sine squared, well, I mean, you could just take that from a formula book or so on, but the standard way to think about that would be a half. Well, you think of sine squared as a half of 1 minus cosine of 2x. So I get an extra half, so it's 1 over 4 pi, the integral from 0 to pi of 1 minus the cosine 2x dx. And now this is just a constant, and cosine, I can integrate it. Except that when I integrate the cosine part, save on space here, when you integrate this, this goes to 0. Okay? When you perform the integral on a cosine, you get a sine function, but then you're only going to, you get sine of 2x, but then you evaluate that at x equals 0 and x equals pi. Well, sine is 0 at both of those values. So cosine part doesn't contribute anything to the integral. And then integrating 1 from 0 to pi just gives you pi. That's just the length of the integral. So this evaluates very nicely to just a quarter. Nice and simple, just a quarter. So we don't need Parseval's theorem to tell us that this integral is a quarter. That just comes from basic integration. What Parseval's theorem is telling us nicely is that a quarter will be the limit of the infinite sum of all those a's and b's with the appropriate scaling coefficients in front of it. So let's see exactly what that sum is. And the reason it might be interesting is because it's mentioning a pi. See, one of the coefficients has a pi within it. But today is International Pi Day, of course. Or American. Everybody know that? Yeah? Pi Day, so just in time. It is appropriate. Let's look at the right-hand side. The right-hand side of Parseval's theorem is a quarter a naught squared plus a half times the sum from n equals 1 to infinity of the squares, the sum of squares of the a n's and b n's. So what is that for us? Well, Ra naught is 2 over pi. So when you square it, you get 4 over pi squared. Take the quarter of it, you get 1 over pi squared. Our b1, yeah, so there's only one b1, and it's a half. So when you square that, you get a quarter. Get multiplied by a half, so you get an 8. And then you get the sum of all the a n's. So I may as well return to the original way we wrote it. We're only picking up even stuff. Yes, this is going to be 2 over pi squared. Yes, we would get minus. And when we squared it, we would get a 4 on the top, but we're taking this half of it here, so that reduces it back to 2 on the top. And we get a pi squared on the bottom from here, pi squared, so we're taking a n squared. And then we got the sum from n equals 1 to infinity of the square of all the parts that's left. This is 1 over 4n squared minus 1, and you're taking the square of all that. And this is all equal to a quarter. Okay, because a quarter was the left-hand side of Parseval's theorem. Well, so what's interesting here is you have these nice rational numbers, a quarter, an 8, the sum of all these reciprocals, nice simple rational numbers, but then also appearing in there you have pi squared, or square pi. So basically just rearranging this to make pi the subject of it. Can we do that nicely enough? Yeah, when you bring the 8th over this side, it leaves you with an 8th on the left. So it's 1 over pi squared plus 2 over pi squared times this infinite sum. And then multiplying both sides by pi squared and cross multiplying by 8 as well. We're going to get pi squared is 8 plus 16 times the infinite sum. Well, it depends how you want to present the final answer. Let's just leave it like this. So square of pi is 8 plus 16. Let's just look at the first few terms of that. So when n is equal to 1, you've got 1 over 4 minus 1, 1 over 3 squared. So the first term there is a 9. When n is 2, you've got 1 over, what's that? 2 squared is 4, so 1 over 16 minus, so it's 1 over 15 squared. 15 squared. When n is 3, it's 1 over 4 times 9. 4 times 9 is 36, minus 1 is 35, so it's 1 over the square of 35. Continuing. So it's another one of these surprising, strange, infinite series expressions for pi, or in this case for the square of pi. And pi, you know, by definition is all about circles, ratios of circumference to the diameter of a circle, and, you know, but who can tell me where the circle and diameter here is on these numbers on the right-hand side? It's not obvious. It's not obvious that the right-hand side should have anything to do with the circle. It's not immediately apparent. So this is another nice formula, intriguing formula for pi. Infinite series formula for pi, or for pi squared. And maybe that's a good enough place to stop on International Pi Day to find out the unit. So I'm seeing some of you for number theory now for the next couple of hours. But otherwise, I'll see some of you in the mathematics tutorial later this week. And we will be doing revision teaching in the 2 weeks after Easter. So we will be looking at past exam papers and looking at other parts of the course in the 2 weeks after Easter. Okay? If I don't see you before then, have a nice break and work hard.